Juliana, the cars. Anyway, okay. So we're going to move to higher dimensions, by which I mean we're going to be looking at math, not just from the circle to the circle, but from the K torus to the D torus. And we're going to always stick with real analytic maps. Okay, so last time, so here the basic question is you start with a function on the D torus of D periodic variables that has an absolutely convergent Fourier series, and we're going to, under this composition, this map, this is, we're going to ask what are those, which mappings take absolutely convergent Fourier series. We're not going to insist on the composition to be an absolutely convergent Fourier series, because we know the answer to that is, intimately connected to this question about characterizing the algebra homomorphisms of the Fourier algebra. So they're only the trivial maps in that case. It's sort of a relaxing condition to be uniformly convergent. Okay, so this is the problem that Gahan had proposed. So the last time we considered the case K equals 1. And this was a result of Alpar. Strictly speaking, he considered the case K equals D equals 1. So you start with the absolutely convergent Fourier series on the circle. You change variables, and you end up with a uniformly convergent Fourier series. And Alpar said, in fact, the answer is yes. To the question. It's quite a remarkable result. His proof was very, very complicated. And we gave a simple proof. Okay, so we introduced very simple, and that allows us to extend not from the circle to the circle, but from the circle to the D torus. And we use just a simple compactness argument to sort of stabilize the some derivative of the phase, which was always large, as the quantitative bound below, and then by Van Corpen's lemma, we're able to reduce it. And together with the Taylor expansion, we're able to reduce it to just a polynomial with a fixed degree, this oscillatory integral with this Hilbert transform singularity, and then rely on this very nice result of Stein and Wagner. So these are the sort of the ingredients that were sort of not really around when Alpar thought about this in 1965, although that was the same year, it turns out. That Stein and Wagner had given us this nice result. Okay. Anyway, so now we want to get to something much more interesting. Again, with the theme that we're going to sort of go into the world that was thought about quite a bit. I was told by a bunch of Russian mathematicians that this was a popular problem to try to understand this problem when K is 2, say. And there was no progress. As we'll see, the oscillatory integrals become horrendous looking. But the point is, there are problems that connect it to Calderón-Zygmund theory. Calderón-Zygmund theory has been developed in all kinds of ways. And so we're going to use everything we know about Calderón-Zygmund theory to solve the problem in higher dimensions. Right, so first of all, even when we go to K equals 2, let's just stick there. I'm talking about functions of 2 periodic variables. What do I mean by a uniformly convergent Fourier series? 2 variables, okay? Because this is about how we sum the Fourier series. And so we can sum the Fourier series in many, many different ways. So for instance, the usual one common way to sum it is just by taking the partial Fourier sums, where I sum the first frequencies up to capital M, and the second Fourier coefficient up to capital N. I'm looking at the Fourier coefficients of my function, and then I'm expanding it in its Fourier series, cosines and sines, with frequency M and frequency N. That's a function of 2 variables. So this is one way to sum it. These are rectangular sums. And I could ask, does this converge uniformly? As M and N go to infinity unrestrictedly. I want to take the strongest possible sense, and that means that the minimum of M, capital N, goes to infinity. But I also could consider the square sums. Okay, so these are just summing here, not in a rectangle, but in a square. So this reduces the complexity of the problem, and it's a one parameter problem, not a two parameter problem. Okay, and so on. I could sum another plot there, which I'm not going to go into. You can keep going here. We can sum all lattice points and a disk of radius r, and let r go to infinity. So many ways to sum the series. And so I'm going to do a little bit of notation here. Not so good. And I will denote I would denote these, let's say by rectangular U rectangular. So these are going to be continuous functions on the circle, such that their rectangular sums converge uniformly as m and n go to infinity, in the sense that the minimum of m and n goes to infinity. And let's also look at, I'm going to also consider square sums. These are the only two that I will be considering in this talk. So that is the square sums. I'm looking at those continuous functions, so when I sum them in a square, this converges uniformly. Okay, so both of these are Banach spaces. Okay, so we can give them a norm. So a rectangular function that has a uniformly convergent Fourier series in the rectangular sense. I can take the supremum of these partial sums, these rectangular partial sums. I take their L infinity norm to function on the two torus. Then I take the supremum over all these sums. And that gives me, and I can do the same thing with m equals to n, and then I would get the square sums, and in any case, all of these are nice Banach spaces. Okay, so this is just some terminology. So let's now, so I'm just going to stick for the moment, although we will talk, I'll just say words about the more general case as we go along. But let me just stick to the case that k equals 2, d equals 1. Okay, so mappings, okay, so back up to that picture, this mappings from the two torus into the circle. Okay, yes?
Does the situation change if you, for instance, sum when parameters are in a ball, Euclidean ball, and you go with reduced?
I know those circles, so we just mentioned that, yes?
Yes.
Yes, what about?
Is it a different problem?
Oh, yes. Every time we're going to see. Okay. So, in fact, that problem is still not understood. Okay. So that's although I have but as we're going to see, the problems for rectangular sums and for rectangular sums are quite different. But the solution is a surprise, complete surprise. Okay. So I can't, and I haven't really thought too much about the spherical sums, the summing lattice points in a ball. So yes, each time you change the how you're summing, you change the problem. So again, let's look at what these mappings look like. So now I'm taking 2 points, e to the 2 pi is, e to the 2 pi it, and I'm going to land at a point on the circle. So this is going to be some real function psi of s and t, as we saw before. I see that psi has a periodic part, which I'll call phi. So this is a periodic function of two variables. And it has a linear part given by a lattice point, L1 and L2. These are integers. This gives me sort of the linear part of this mapping. Okay, so for every mapping from the circle into the, from the two torus into the circle, has these two components. Capital phi has a periodic part, and it has so sometimes we'll just denote this as phi, and this L bar is denoting the two integers that's giving me a lattice point. To the pin in Z2. Okay, so if we start with a function with a absolute convergent Fourier series of one variable. In general, if I take D to be bigger than one, I have to, now I'm looking at an absolute convergent Fourier series of many variables. But let's just take the simplest case here. So I mean by this that the Fourier coefficients are summable. And we have here that the composition, what does that look like? Composition, which will now be a function of two variables, it becomes the sum of these coefficients e to the 2 pi r n times psi and t. Because I sum overall. Okay. And so just as before, the basic problem that we're going to be interested in, and again, these are going to be depending on exactly how we sum, the problems are going to be different. I'm only going to concentrate on these two basic ones. So the basic problem before is to understand for which side we will always remain in the real analytic category. I'm not going to consider anything different. Is the following control? Is the fact that when I take the supremum and I compute all the Fourier partial sums of this single pure oscillation e to the 2 pi I n times psi, and I compute it, again, let me write this with a question mark, okay? So that could be either rectangular, it could be square, it could be summing tight circles. Now we're in two variables here. When is this finite? So let me tag this as star question mark, where this means really in this talk, either I'm going to talk about rectangular sums or square sums. But I can go on. Okay. So that's the basic problem as before. So again, once we unpack this, we see, of course, this means that I'm looking at a certain oscillatory interval. So let's take the supremum. What is the supremum? Okay, so now I'm going to take, this is quite a large supremum. I'm going to take let me just, I'm going to just do this with, let me just stick with a rectangular. And then all you have to do is put capital M equals capital N for square. Okay, so what does this thing look like? I have convolution, so I have this rectangular partial sum, so that's just convolution with a product of Dirichlet kernels. So now I have a double integral over the two torus. I'm looking at e to the 2 pi I, and then I have here n, and then I have phi of x minus s, y minus t is convolution, and then up to I'm going to be taking absolute values. So I'm going to, then I have this linear part. Some of it comes out with modulus 1. So L1 of s plus L2 of t. And then I have the product of these two Dirichlet kernels. ds dt. And so we're taking the supremum and x and y and m and n, and capital N, little n, and x and y. So lots of parameters to try to see when this is finite. Okay. So the problem is getting a little bit more complicated. How do we understand this at all? Okay, so I'm just going to take you through some bits of inspiration. Okay, because it took me a long time to sort of figure out exactly what's going on, but there's a lots of help along the way. So the first bit of help that we're going to look at is coming from Charlie Peppermint. So let's look at this wonderful result of Pfefferman from 1971. Old results. He wrote nice papers back then, very short paper. And I'm going to give you the full proof that he proved that there exists continuous functions on the two torus. Okay, so multiple Fourier series. He summed it in a rectangular sense, such that that the sum, the rectangular sum of f diverges as m and n go to infinity for all points on the two torus. So that was a remarkable result. In the same paper, well, actually no, but if I remember this correctly, these were papers, both very, very short, side by side, same issue, both in the AMS, 1971. One paper was to show that for L2 functions, when m and n are the same square sums, you get convergence almost everywhere. So it had a very clever trick of reducing it to the one-dimensional case. And then he proved that when you think about rectangular sums, then nothing good, right? Continuous functions diverge everywhere. I'm going to show you the proof, because this is the proof that's going to start to help us think about where is it, this monster. Okay, so what did he do? I just want to give you the heart of the matter. I want to just, okay. And I'll give you all the details. Not that he actually goes in a very short paper. He comes somehow really did all the details. Maybe because maybe he wasn't certain exactly about these oscillatory intervals. They're a bit subtle. So he started by considering the function, this pure oscillation, e to the 2 pi I lambda x times y. That's how he started. Okay, so like a hyperbolic. This is going to be the key to understand what goes on when you understand a hyperbolic oscillation. So this is not periodic, of course, but he's going to construct a periodic function, a continuous function, by taking these guys. I'm going to think of x and y, say it's quite, so I have some fundamental domain that we repeat periodically. So I'm saying, well, within the fundamental domain, it's going to look like this. And then he's going to put these guys with various sequence of lambdas. As lambda goes up to infinity, and he puts them all together in a smooth way and constructs a nice continuous function, okay, in the limit. So this is the key, is to understand the partial sums. We need to understand this rectangular sum, S, M, and N, of this G lambda at some point X and Y. So we write this all out. And so I have this double integral over the 2 torus. I have this e to the 2 pi I. I have lambda of x minus s and y minus t. This is a convolution of this pure oscillation against the product of these two Dirichlet kernels. So that is the partial sum. Okay. We want to understand, does that grow? Can I uniformly bound this in all the parameters or maybe not? And the point here is you can guess, because this is a rectangular sum, we're going to see that this is not going to be uniformly bounded. So we're going to want to bound this from below. So let's take our time. So let me multiply this out. Now, first of all, recall there's so this behaves like e to the 2 pi I, and we have this linear oscillation over s. Not exactly this. It's sine of 2 pi I of m plus a half times s and over sine of pi s. And so what we're going to do is put these in. There's 2 terms here if you do this precisely. And then, so this splits into actually 8 integrals. Okay. So there's going to be, so first of all, there's going to be, let me do it here. So there's going to be a pure, so there's an e to the 2 pi I lambda times x times y. When I multiply these two together, that comes out of the integral. Okay, then I have here e to the 2 pi I, that is some mixed terms, but then I have this s times t. So I have this double integral. And now I'm going to think about this in the principal value sense from minus a half to a half, minus a half to a half. E to the 2 pi I have lambda times s times t, plus, then I'm going to have the mixed terms here. I'm going to have here, let me get this right. I'm going to have the lambda of y plus or minus m. That'll be the linear oscillation. So this is e to the 2 pi ms plus or minus. There's 2 terms here. Okay, and then I have a lambda y that's coming from here. Okay, that is multiplied to s. And I similarly for the t, I have lambda x plus or minus n times t. And then I have here 1 over s, 1 over t. This is now a double Hilbert transform singularity. Instead of, so we're having this oscillatory integrals to the point, but my amplitude now is a double Hilbert transform singular kernel. So again, it's a game of understanding how the cancellation that arises in this oscillation, how does that combine with the cancellation that arises from this double Hilbert transform singular kernel, and plus O of 1. Okay. So there are 4 integrals here, I've written sort of hidden here. So each choice of plus or minus arises. There are 4 choices for plus or minus. So 4 integrals here, 4 integrals there. Okay. So when I'm multiplying, and so you have to check, or you have to believe me, that the rest of it is uniformly bounded in all the parameters. Okay. So let's keep going. Now the point here is I'm going to fix now. I'm going to fix lambda large. I'm going to fix lambda. I'm going to fix x. I'm going to fix y. Give it a lambda x and y. Notice I can find a choice. There exists a choice of plus or minus. There's 4 choices altogether. What I want to do, here's the enemy. So he's trying to get this to be large. And if this, so these are linear oscillations, and they're much stronger than a hyperbolic oscillation, as long as they're on equal footing. So whenever this coefficient, I just think one of these coefficients to be at least as large as lambda. So n can be very large compared to lambda, or n can be very large compared to lambda, or it can be very small compared to lambda, okay? Then I would get an O1 contribution. However, there is a choice, of course, where I can completely cancel this. Okay, strictly speaking, m is an integer, n is an integer. These are not necessarily integers, but depending on the sign of lambda y and the sign of lambda x, that's going to give my choices. I can find 2 integers, which is within a distance 1. So this sum is O of 1. Okay, so there exists a choice and a choice of 2 positive integers n, such that we have that these quantities, these linear oscillations, cancel. So this guy and lambda x plus or minus n is O of 1. Okay. Now, whenever I take this choice, add that n and n. So y, lambda, y, and x are fixed. Now I choose my m to be more or less, suppose that this is positive, then I would just take it to be the integer part of lambda times y. Okay. And similarly, so I've made my choice of m and n. Given the choice of m and n, then for all other choices of these signs, at least one of them has to be of the size of lambda. Okay, so being on equal footing with the size, and it's a linear oscillation which is much stronger than this hyperbolic oscillation. So all of those other, so 3 of the integrals are going to be O of 1. And I'm left with 1 integral here. And so I carry on the analysis here. This is equal to, I have this constant of modulus 1, which I'm not going to think about too much. And then I have this principal value integral integrating from minus a half to a half, minus a half to a half. I have e to the 2 pi I, lambda times s times t. I have plus cs. So my c is this choice. Plus eta t. My eta is this choice. Both of them are all 1. They're at most 1. This is large. Okay. So times integrated against ds over the double Hilbert transformation plus over 1. Okay. All the other ones, all the other choices of plus or minus with this choice of m and n means that these linear oscillations, at least one of them is of the size of lambda. A very easy argument if you want. I'm happy to walk you through that, but you get O of 1. Pfefferman in his paper seemed to be a little bit unsure, and he gives all the details. amazing. Yeah. Very rarely do you see that in a 3-page paper. It's all. Okay, so now let me finish this part of the matter. So we have here.
Could you please explain one more how you choose M?
What's that?
Could you explain one more how do you choose M?
Okay, so I have, so here I have, so I'm gonna fix lambda and X and Y. I fix those, okay? Now, suppose that these are both positive, say, I don't know if they're positive or negative. But they're both positive, then I'm just gonna choose M to be, I'm gonna choose this to be the minus sign and M to be the integer part of lambda Y. I'm gonna choose the minus sign here and N to be the integer part of lambda times X. So that there are numbers between 0 and 1. They're all 1. That make sense?
Yeah. Then how it helps you to get SAR? Like how it helps you once you get that M? How is it helping you?
You want to get this because the point is that this oscillation, the linear oscillation, is much more is stronger than a quadratic. In this case, a hyperbolic oscillation. Okay. So the enemy here, what's going to give when this dominates? So if these coefficients are at least as large as this one here, one of them is at least as large, then it's over 1. It's a very easy argument. I can show you that. Okay. You have to buy me a coffee though. And then all other choice. So this is I made this choice, and they're both small. They're both over 1.
Okay.
All other 3 remaining, at least one of them is at the magnitude of lambda, and therefore these are all over 1. So I'm stuck. I got over 1 up to over 1. I have this particular linear oscillation, but both of them are now C and eta are now over 1. Okay. And now I can remove them. So the next step is to remove these two. So again, I have this constant, I have this principal value, I have this minus a half to a half, minus a half to a half. I have e to the 2 pi I, lambda times s times t. I can remove this linear oscillation up to an error term of over 1. Again, very, very easy, kind of very standard these days, but Pfefferman writes it all out, the details. It is 3-page paper. So if you're interested in this simple reduction, very simple, I'm going to show you that again. Coffee break. Very simple. Now it's just calculation. So this is just a sine interval. Cosine goes away. Okay, so it's a sine interval, sine of lambda st ds over s from 0 to a half, 0 to a half. Make a change of variables in one of the integrals, u equals lambda st, and off you go. And you see that this is in fact a constant. A constant times log lambda plus O over 1. And this constant is non-zero. This is the heart of the matter. Okay. So it's this hyperbolic oscillation which is behind that makes this. Now notice I needed 2 parameters. I couldn't get away with this square sum. I needed both to kill these things off. Okay, to make both the linear terms of the has a small all 1 frequency. Okay, wonderful. That's the heart of the matter. Now we need more of it. Okay. And then Pfefferman just glued this together. Glued this together and came up with this continuous function there. Now, we're going to, this actually helped us, Pfefferman's result in thinking when we go to looking at an area, a well-developed area, multi-parameter Calderón-Zygmund theory. Okay, so this is a huge now, well-developed area of Calderón-Zygmund theory, started with the work of Journet. Now we're taking kernels that are Calderón-Zygmund kernels that kind of look like this double Hilbert transform singularity, 1 over s times t, and so we develop this theory. But remember this other aspect of Calderón-Zygmund theory, these singular integrals along these curves, which are called generalized Radon transforms. That was very important in the development of trying to bring Calderón-Zygmund theory to try to go from elliptic analysis to parabolic analysis. Now, one does the same thing here. The history of this operator is a little bit different. Now I take a function, again, of two variables, very similar, but instead of integrating along the graphs, this is now going to be, I'm going to go along the surface. So this is going to be an operator of functions in R3. So I'm going to look at a double interval. Again, principal value, to define the principal value sensitive, you define it as a tempered distribution. And you convolve it with this tempered distribution, you get x minus s, y minus t, z minus phi of s and t. You're integrating ds dt over s times t. So that becomes a basic. Now this is one of the first sort of singular integral operators for these Radon transforms, but now it's in the two parameter setting. Interestingly, this question actually came up from a problem. We started to think about this question coming up. It's a question of Michael Cowling. He had a particular problem about representation theory in Lie groups. And in particular, he was thinking about this Hagroot constant and that's finite. And so he came to an oscillatory integral that's very similar to the multiplier. This is convolution with the distribution. And therefore, it has a multiplier. So on the Fourier transform side, if I look at this, I look at this operator on the Fourier transform. Now this is a function. This is now frequency variables are 3. So this is a multiplier depending on this graphing function c eta gamma times the Fourier transform of f. And then if you just want to understand L2 boundedness, that's always the first thing. I want to understand when is this multiplier is a bounded function of the three frequency variables. And it is a oscillatory integral given by a principal valued interval. I'm integrating e to the 2 pi I, gamma of phi of s and t, plus cs, plus eta t, ds over s, dt over t. And I want to understand when is this a bounded function. Looks similar, doesn't it? Right? Except I don't have this extra translation parameter, x minus s, y minus t, when I'm looking at this problem that came from the 1970s. Now, this is a problem that people studied in the 1970s. So I don't know if I've rubbed off the have I rubbed off the singular integral? No, here it is. No, where is the original? Did anyone see it on the board? Maybe it didn't. There. Okay. See that? Take a look. Similar. So we studied this very intensely. And so here is now what's interesting now, we have a theorem. So what's important here, turns out, is to look at the so-called Newton diagram of this function of two variables. So I'm going to take my function and let's look at it. Now I'm just interested here because S and T are small. S and T are small. So I'm just interested in what's happening for small s and t. So I Taylor expand it. And I get a polynomial, I get this expansion in terms of monomials. Okay, so I plot. The idea here is to understand what's going on with this oscillatory integral and this was, by the way, this goes back to work of Arnold and Barchenko, that to understand oscillatory integrals of phase functions of more than one variable, in particular two variables, what they were interested in. You want to look at the Newton diagram. That means I plot all of these points. I plot all the points that arise in JK space. Which coefficients are non-zero? Of course, there could be many of them, okay, in the space. And what I want to do, what's going to be relevant here are the positive quadrants of each guy here, because that's going to represent the places where this particular monomial, for these J's and K's, that's going to be the places where that monomial dominates pointwise the scene. And so therefore, to understand what's really going on, I need to look at all the positive quadrants and take its convex hull. But take its convex hull, and I get this huge unbounded polynomial region, which is called the Newton polygon. Okay. And so things depend on it, for instance, how the scalar, they were interested not in this type of oscillatory angle, they were only interested in, say, let's take C need to be 0, no singular amplitude here. They want to know how it decays in gamma. You can read it off by the Newton diagram. Okay. Here, we're asking a different question. How does this oscillation, how does the oscillation, cancellation from oscillation, how do I marry that with the cancellation against the double Hilbert transform? And you have this nice theorem, which I think is somewhat nice. You have a theorem that says that this guy is bounded in is a bounded function in R3, if and only if, for every vertex, J comma K in this Newton polygon. So I'm just looking at the picture, these are the three vertices, they matter most. Okay, so some sort of linear combination of these guys control everything else by convexity. So for every vertex, we have to have that J times K is even. That's the result. Okay, so what do I mean by J times K being even? I mean, it's a bad vertex if they're both odd. If at least one is even, we're good to go. If they're, I need to check this for every vertex. If there's a single vertex where they're both bad, then this multiplier is unbounded. Okay, all right. So this is gonna, and so let's look at some examples. Let's look at Charlie Pfefferman's example, S times T, this hyperbolic. He just had the single, hyperbolic oscillation. What is its Newton diagram? Well, there's just one point here, 1, 1. Okay, and so the Newton diagram is just this thing here. That's the only vertex. They're both odd. That's bad. We saw that. Okay, it grows like long lambda. Okay, that's Pfefferman. Okay. Okay, however, you could let's look at another, which was this is an important one from sort of our perspective. What if I look at AS plus BT squared? Something like this. Okay. So here there is going to, when you multiply this out, I'm going to have so this is the Newton diagram. This, if I look at this, I'm going to have a vertex here at 2. I'm going to have a vertex here at 1, 1, and I'm going to have a vertex here at 2. And so you see here this 1, 1 bad vertex, but it's in the middle. It's in the middle. I really should be dealing with colored chalk at this point, shouldn't I? But anyway, okay, you can. My pictures tend to be simple. Okay. So there's the Newton polygon in this case. I have here I have these 3 points, but then there's only 2 vertices, and they're both good. This was actually good. Okay, so we get this uniform bound. Okay, so this is not the enemy. So the point is that when we start to think that life is going to be much more complicated, let me remind you. We're going to be looking at this function for every x and y. For every x and y. So that means I'm going to be looking s and t are small. S and t are small. So really I'm taking this real analytic function phi, and I'm going to Taylor expand it around x and y. That's sort of the key thing to look at. Right now I'm going to be looking at this Taylor expansion. J derivatives of this phi at x comma y, then I s to the j, t to the k. My Taylor expands the idea. This is my phi of x minus s. Okay, we're getting factorials, like plus or minus 1 signs. Okay, and so notice that the Newton diagram, I need to understand this for all x and y. The Newton diagram is changing. Depends on the point X and Y. For every X and Y, I get a Newton diagram. And so I need to understand the Newton diagram as I vary the Newton diagram here. This guy is highly unstable, highly unstable. Okay. Because if you just perturb it ever so slightly, the Newton diagram is jumps on you. Okay. Now it jumps in the correct direction. Okay, there's some semi-continuity here. Okay, so if I look at these are the places where the partial derivatives at the origin, but then eventually I'm going to have to be looking at the partial derivatives at a certain point x comma y, and that's going to vary. So all of these points represent where this partial derivative is non-zero. So in a neighborhood, as I perturb it, they still remain non-zero. But then additional ones could appear. So this jump, it doesn't jump in this direction, it jumps in this direction. Okay, that's called upper continuity or lower continuity, I forget which. Okay. And so we need what is the enemy here? We need to understand this thing, expansion, and we're going to need to understand what's the enemy? I want to know whenever the mixed second derivative is, so I want to make sure that whenever the mixed second derivative is non-zero, both of these better be non-zero. Okay. In order to give me a Newton diagram that's good. Okay, so keep that in mind. So that is what we need the fact that this is somehow, whenever we vary, we need that whenever the mixed second derivative, that's the enemy, that's the hyperbolic oscillation, when that is non-zero, it better be that these two guys, both, if one of these vanishes, then the Newton diagram becomes this. And this becomes a vertex. It's bad. So whenever this is non-zero, mixed second, these guys have to be both non-zero. Keep that in mind, and let me rub off the boards. Okay. Okay. So let me give me a couple minutes. Wait a minute. Is one board empty? Have I did a silly thing? Okay. I don't really have too much more to say, but thank you. Okay, so we still need a little bit more help. We still need a little bit more help. Okay, so we really need, and this is the last bit of help comes from this wonderful theory that Brian Street, about 2008 to 2015, wrote a series of papers, including a book on this multi-parameter Calderón-Zygmund theory with respect to these singular radon transforms. So they went from the translation invariant cases I wrote up. So this which I rubbed off. You see here. Do you remember that translation invariant H sub phi that has that multiplier that does not depend on x and y, did not have this translation bit to it. So that was, of course, that is a multiplier, comes from a translation invariant operator. But now we're putting in this translation that is going to make all of these, that makes all of these, that becomes dependent on the point x and y. Therefore, the Newton diagram is changing, jumping around. And so we really need to understand not just simple translation invariant multiple parameters Calderón-Zygmund theory with respect to the singular random transforms. We need to look at this work. So they go to general, non-translation, okay, if you like, non-translation. Quite, I mean, there the subtlety now, it's this cancellation. Remember, these singular integral operators are no longer bounded on L2 necessarily. We have to understand what is the right cancellation. We did this in terms of this Newton diagram. In the necessary and sufficient conditions are about the vertices, and it has to be the case that every vertex has to have at least one even component. Okay, so they're much more complicated. So they're now in these non-translation invariant settings. And so at the base of these operators are vector fields. Okay, so you think about these vector fields. These are just our partial derivatives of our phase function phi, our partial derivatives. Okay, so there's these vector fields, and what they need to understand, they came up with a very satisfactory when are these bound on L2. They figured out the cancellation in terms of these vector fields. So they said that whenever the pure vector fields, they have this notion of a pure vector field, that for us is a pure derivative in either a pure derivative in S or a pure derivative in T. Okay, so the bad things are these mixed vector fields, which for us are the mixed derivatives, in particular this hyperbolic, the partial derivatives with S and the partial derivatives with T. These are the bad. We need to be able to control the bad ones, the mixed vector fields, in terms of the pure vector fields. Okay. And so this is the hint, and that gives us, we need to control somehow all of these mixed derivatives in terms of the pure derivatives. And we start with just the second order derivatives. So we have a definition. The definition here. Now, okay, let me rewrite. We're looking at these oscillatory angles. They have this form of phi of x minus s. There was an n here again. Y minus t. And then we had some linear stuff. And then we had this double pivot transport singularity. Okay. So it's this thing here. So we need to be looking at this this phi of x minus s before, y minus t. I expand, I have all these mixed derivatives of phi at the point xy, s to the j, t to the k. So we need to, so here we have this definition, which I call the factorization hypothesis. So I take my phi, here we go. This is a real analytic function of two variables, real analytic, periodic, and I'm going to call this, let's say it satisfies the factorization hypothesis, FH, if for at every point, x, y on the two torus, these is germs. I take the mixed second derivatives. I take the mixed second derivative of phi. I take the mixed second pure derivatives, and they have to divide. The mixed second derivative, the enemy, as germs of real analytic functions. So that this is in the sense as germs of real analytic functions. It's just a nice language. When you look at analytic functions at a point, to understand it, you need to understand an analytic function. I need to understand all its derivatives at that point. So then that makes that understand in some neighborhood. And you can quantify, put all this nice in a ring structure. A germ of analytic functions is a ring. And so this is divisibility. I mean by this divides this. So it's a multiple. So this mixed second derivative is a multiple of this. That just means it can multiply by some analytic function in the neighborhood of that point. And notice, this is exactly the right thing. First of all, it's right in two ways. It's if this guy, okay, if this is non-zero, then necessarily these two have to be non-zero. Okay? Because if one of these guys vanishes, that makes this vanish by this divisibility. So this is taking care of the enemy. Okay? This Newton diagram is always going to be, if I do have that problematic hyperbolic oscillation, then the Newton diagram is always has to be including the two corner points. And so things are good. Not only that, but it meshes well with the sign-street theory, because this condition allows me, from this is very easy, a dilemma, that I can control every pure mixed derivative, higher order pure mixed derivative, in terms of the pure derivatives and as the pure derivatives in T. Very simple calculus exercise, okay? And you can quantify exactly how you can control that. So this is exactly following the sign-street idea, and that's going to give us the Wright cancellation condition. Theorem one. Okay, this star rectangle, okay, holds if and only if, okay, phi satisfies factorization. If and only. Okay. So we certainly see examples where the factorization hypothesis is not satisfied. Okay. And we see examples where it is satisfied. And this gives us exactly the necessary and sufficient condition that solves this problem. Now remember here, this is this phi, this is the phi that comes up. When I look at my mapping from the two torus, this is a mapping that depends on this real analytic periodic function, but it also has this lattice point, this linear part. So this is saying that it does not depend on the linear part at all. It's not. It says that it only depends on the nonlinear periodic part, and that guy must satisfy the factorization hypothesis, if and only if. Theorem two. For every, by the way, I should maybe this, although this is dated, this is solving the problem for mappings from the two torus and the one torus, but this easily extends to higher dimensions, mapping from the two torus into the D torus, just as we did before. Remember, in that case, we had a D tuple of real analytic functions, but now of two variables. So we put them together as a D tuple of real analytic periodic functions of two variables, and I take the dot product of that with a point on the unit sphere. This is part of one of my parameters. This was the key guy to consider last time. And then if I'm looking at this function, which maybe I'll call rho, the function of all of these variables, including, so this is I'm looking on this compact real analytic manifold, just as before. And the theorem, I'll just tell you in words, the theorem simply says that this guy into now from two torus into the D torus satisfies the rectangular problem if and only if this guy satisfies the factorization hypothesis. But on this manifold, that means for every point on this compact manifold, I look at the pure second derivative in S and the pure second derivative in T, and that has to be divide the mixed second derivative in S and T as germs of analytic functions. But now it's analytic functions on this compact manifold. So that's the higher dimensional expansion. Now, interestingly, now let's compare it. And of course, Jacek is going to ask me what happens on spheres, with our balls, and I don't know the answer to that. But here, for every real analytic mapping, remember this is given in terms of this real analytic periodic function of two variables and a lattice point. So every mapping from the torus into the circle, real analytic. There exist infinitely many. So for every real analytic, forget about this factorization hypothesis now. That really was about the two parameter case. There exists an infinitely many lattice points such that the corresponding guys, so for every phi, there are infinitely many lattice points such that the square sum problem holds. And of course, the final question you want to ask is, well, what about can it fail ever? And the other part, so this is part one, and the other part is that there exists a real analytic phi. There exists a real analytic phi from the two torus into the real analytic, such that this problem fails for some lattice point. Okay, so for every real analytic phi, I can find infinitely many lattice points for which this problem is true. So this problem is sensitive to the linear part and the square thing. Very sensitive. And there exists, however, real analytic functions where I can find. So I know for this guy, there are infinitely many by part A where this is true, but there's at least one where it's not true. Okay. And I will leave it to you to sort out what happens for spherical sums. That seems to be, if you write that down, now we're talking about Bessel functions. And as you guys know, I don't know anything about Bessel functions. All right, so let me finish there. I didn't want to take this long walk. I wanted to get into, but I'll leave I want to talk about a completely different problem. I'll do that tomorrow. Okay, thank you.
Any questions? Marco?
So, well, you said that for the circle you don't know, but like for
Yeah.
for sphere, yeah. But for ellipses,
What?
for ellipses, can you, because like rectangle, I mean, if you allow rectangles, you fail.
You can. Yeah, but that's even much more difficult.
More
I'll give that to you as a problem. You have the one for just spheres, and you can. Yeah, that's good. Yeah, that. Good question. Let's figure out what's happening with the spheres first.
But if it would be easier then. I mean, I expected fails, and I mean, like as before, when you go
Yes.
you fail.
Yes, it certainly will fail, right? But then to figure out exactly when it fails is I mean, so this is somehow a surprise for me that actually there's a theorem out there that you have this if and only if this. You have this control of it's all about the mixed second derivative, the second order derivative, sorry. Right, I want to ensure that whenever the mixed second derivative is non-zero, those other two guys better be non-zero. So as soon as one of those pure derivatives vanishes, then the mixed derivative has to vanish because of the divisibility. And that's the key thing. And now, by the way, I can also do this problem. You might ask, well, that's just k equals 2. What about k equals 3? Now I have 3 variables. Okay. And that's something I've worked out as well. And that's much more complicated. Now the third order derivatives come into play. Okay, so you have these conditions. By necessity, you have to deal with the second order derivatives, but now I need to control somehow. I need to control the third order. I need to control the pure. In fact, it's the pure third order derivatives. If my variables are s, t, u, if I take the pure third derivative in s, t, and u, okay, I need to be able to control that by the pure derivatives, third order derivatives. So the pure third order derivatives have to divide this pure mixed derivative as a germ analytic function. So that's the added things together with all, because once you're in 3 variables, it's very easy to see that you can just fix one of the variables and you solve the problem in the other two variables. So you automatically get, when you have no necessary conditions now, for any freezing one variable, I look at the other two, that gives me these necessary conditions in terms of this factorization, in terms of the second order derivatives. But then the thing that puts them all together is I need something about the third order derivative. And the enemy is that pure third order derivative.
Yes.
And that's the additional hypothesis that gets used for that, okay?
So do you mean that there is a third three-dimensional version of
Yes.
this? There is.
Yeah,
So
somewhere on
for
my desk.
instance, you can then apply it to.
Somewhere on my desk. It's that, yeah. I mean, my wife is threatening that she's burning that stuff. No, yeah, by the way, all this is unpublished stuff that I did years ago.
So the three-dimensional version of Peppermint rectangles
Yes?
can be solved, can be
Oh, yes, yeah. So that's the key thing. One, so, yeah, okay. So yeah, so that's because it's once you know it's in two, then it's automatically it's in three independent. In fact, you can easily show that if you take two frequencies and a square and a third one independently, then that has to be divergent as well. So any two parameter version, you will be able to find a continuous function where those three sums diverge. Okay. The key is to understand the two-dimensional case, just for this example. Okay. But as I said, I don't know n squared. Who did I leave that problem to? Like you, all right? Yes, right.
Any other question? So yeah, thank you, Dean, and let's have a very happy 10:30.